In this video, we are going to focus on rigid bodies.
Right. Without rigid bodies, there is no physics simulation.
That's right. Now, we've already defined what a rigid body is, but as a quick reminder, in case you forgot from one video to the next, it is simply a non-deforming object and that's the important part, non-deforming object that listens, and I'll just draw an arrow, or it responds to forces and collisions. Also joints, but we'll talk about joints a little bit separately. The big thing is going to be forces and collisions. Now, in order to, well, before we go into what's required for a rigid body, let's just talk briefly about this whole non-deforming aspect with a couple of illustrations. So, if I have a sphere, and let's just assume that is a perfect sphere. The idea of a rigid body is that no matter what I do to this sphere, it is always going to retain its shape. So if I was to slam it into a corner of concrete as hard as I possibly can at like 100 miles per hour, that wouldn't matter. It wouldn't dent, it wouldn't fold, it wouldn't bend or break. It's always going to retain that initial shape.
Right, and that concrete curb corner wouldn't dent, chip, crack, nothing.
That's right. And because of that non-deforming nature, these objects are very simple to calculate. And that's why you can have a lot of them in most of your games. Now, scribbling away from that for just a moment, let's talk about what is required in order to have a rigid body. You need, at the very least, the bare minimum you can get away with, is a game object that contains a rigid body component
and one of the collider components.
Mm-hmm. That's it.
It doesn't even have to have a mesh renderer or a mesh. So you could have a rigid body that you couldn't see in the world.
And you can technically get away without the collider and just have the object simulate. I mean, it could just fall based on gravity. It could be pushed around based on forces. But it couldn't bump into anything.
Right.
So, I mean, I guess...
Not very useful.
Yeah, I guess, saying that it's absolutely required is a little bit of a stretch, but I just can't imagine doing anything pertinent with rigid bodies without having a collider. And then as soon as I say that, I come up with, like, multiple examples of it. Like, if you just needed the information of velocity or force calculations, you can do that. But in most cases, let's keep things very simple, because you can come up with an exception to like every statement out there, and I know that. But generally speaking, your rigid bodies are going to need to have a rigid body component and a collider. Now,
right. So the person who just opened up and started firing off their PM, yes, there are exceptions.
There are exceptions. There's an exception to everything. That's just what we're going to go with for now. There's an exception to every rule except for this one. And now, the next thing I just want to throw out there is that if this is all you have, then you can't see anything. Because a collider, as we all know, is an invisible surface. So in your game, that wouldn't even show up. You can still do some interesting things like that, but nothing that would affect the player visually.
Right.
So,
and we'll actually take advantage of an invisible collider that you can't see anything with when we get the cloth.
Mm-hmm. But if you want to be able to see what's going on, you need some other things as well. You need some sort of a mesh, which of course would come to you by way of a mesh filter and a mesh renderer. So I'll just go ahead and put that in. So mesh filter to store whatever your mesh is going to be, and of course a mesh renderer so you can see it. And then finally, you're going to need some sort of physic material. And this one especially is optional, but highly recommended. I mean, you can get away without it. You can simulate a rigid body without a physic material. I just wouldn't recommend it. Always try to throw something in there.
Right. If you don't have one attached, there are default settings that the system uses.
Yeah, but who wants to use defaults for everything? So these are the things that 9 times out of 10 you're going to need. And like we mentioned a second ago, I'm sure we can come up with special situations where you could remove just about any one of these. But really, if you're going to do some sort of physics calculation involving rigid bodies, you at least have to have this one. All the others are kind of up in the air based on really particular circumstances. But if it's going to be an object that you want to see and you want to have bounce off of other objects and you want to have it respond in a particular way in which you can control its friction and its bounciness, then you need all of these things. So let's go ahead and set one up, and then we'll take a look at some properties. So I'm going to jump into Unity, and here I am inside of our little basic snow world. And I've got our little campsite. I'm going to squeeze some things kind of out of the way. I do want to point this out, and I'll probably have to mention it again before the videos in this section are done, but I have loaded in the Physics Materials package that is included with Unity. Later on, that will become very handy. As a matter of fact, I'm going to be using some of them right here in this video. It's already included. If you haven't loaded it in, of course, it's just a matter of going under Assets, go over to Import Package, navigate to wherever you happen to have installed Unity, and if you go under Editor Standard Packages, I believe, you'll find it, and you can load in the Physics Material package. Okay, now, with that out of the way, let's create our own rigid body. So I'm going to start off very simply. I'm going to go under Create, and we will make a cube. And of course, this cube is kind of sitting down through the ground, so let's pull it up out of the ground. And we'll put it over here where we can actually see it. And it looks great. What a fantastic cube. But I'd mentioned earlier that, of course, we want some sort of a collider, and to keep things interesting, I'm going to right-click and remove our box collider. And let's jump back over to our list, and then we'll take a look. We need a mesh. Check. We've got a mesh. Now, we need the rigid body component to be on here as well. So let's go ahead with this object select, go to Component, jump down to Physics, and we'll take a look at rigid body. And we'll drop that on. Now, rigid body has some properties I'll be talking about in a minute. Right now, this isn't completely set up. So let's jump back over to our list again. So we've got a rigid body. We've got a mesh. Now we need some sort of a collider. Now, I just had a box collider on there.
Right. Well, do you want to show them what happens if you don't have a collider?
Sure, if you want to. We can just go ahead and hit play right now. And did I already lose it? I think I already lost it.
Yeah, it's gone already.
It's already gone. So here's what I'm going to do. I'm going to pull this a little bit further up into the air because as we saw when we took a look inside the Physics Manager, which is under Edit, Project Settings, Physics, we already have gravity applied, which means as soon as you designate an object as having a rigid body component, it's already going to be listening out for gravity.
Right. There's a master force, that being gravity.
That's right. So if I grab this, and oh, there it goes. We just barely caught it, and you probably didn't even see it because we're only capturing at 10 frames a second. So I guess...
Well, we could slow gravity down.
We could, but I don't want to. I like how fast gravity's going. What I'm going to do is just figure out which way we're looking, and I'm going to solve that problem and just make us look back at the campground, and that should make things a whole lot easier. And there it goes.
Yep.
Right
so
down to the floor.
it's got gravity applied. It's falling down, but because it has no collider, it doesn't interact with our world.
That's right. So let's go under Component, go back to Physics, and we have some colliders to choose from. And I'll be talking more about colliders specifically in an upcoming video. Understand, though, a lot of these different components, a lot of these properties and settings, they're all kind of interrelated. And so it can be kind of fun talking about only one thing and not talking about other things as well. So here we've got to throw in some sort of a collider. Just for fun, I'm going to put a sphere collider on here, even though this is a box.
Right. There's no rule that says you can't use a different collider with your object. You use any collider you want.
Absolutely.
The physics engine is going to use whatever collider you choose to determine what calculations it gets, which can yield some very interesting results.
That's right. And finally, we need some sort of a physics material. And I say need because I want you to remember to put one in here. You don't absolutely have to have it. We can hit play right now. And our box will fall, and it will start to roll in a really interesting way. And that's because the physics system is looking at this box as if it was actually a ball. But it looks to us like it's a box, so you get this really cool kind of squashy sort of roll effect. Now, what I'm going to do is come in here to our physics material. It's right here with the material property. We'll click our little load button. And because I have already loaded in the physics material package, it finds these assets, and we can choose from some of the prefabricated ones that come along with Unity. We have a bouncy material, we have ice, metal, rubber, and wood. So let's grab rubber. So now we've applied a rubber material, and we'll hit play again. And now we're behaving as if that was a great big piece of rubber that just hit the ground. Now if you were expecting that to bounce, well, by default it's not going to. We can change that. I'm just not going to talk about that right now. I'm not going to let myself get sidetracked because really I could spend a lot of time.
There is a little bounce there, but it might be hard
minimal.
to see.
It's minimal. Now I'm going to do something kind of fun. We're going to take this guy and move him really close to this slope. And then, because I'm sure if I don't do this, I'll regret it, we'll take our first-person controller. And by the way, if you don't already know, this is just the first-person controller that comes along with Unity, which is why this is so basic. So if I hit play now, and we can watch our little guy roll around. And then he'll roll back. So obviously not the ideal collision for a box, but it does look pretty cool. And with that, we have set up a rigid body. Now what I'd like to do, to kind of bring the video, bring it home, so to speak, kind of bring things to a close, is let's take a look at the properties found within a rigid body, because there really aren't that many, and they're all pretty simple. First, we have mass. This is the weight of your object in kilograms, just like mass in the real world. So we could set this to 5 if we want, and now this is a 5 kilogram block of something that vaguely resembles rubber. Now, there are some rules. The documentation warns you that you should not have any object that is 100 times greater or 100 times less than the mass of any other object in your scene, especially if the two are going to be colliding. And there's no reason actually given. I imagine it's because you can run into wild velocities and unforeseen results. Problematic results. We'll just leave it at that. So mass is going to be your weight. Next, we have drag. Drag is going to be kind of an air resistance. It's how much counter and so how much anti-force is applied to your object while it moves. So if we set this to 0, we get no drag whatsoever. We have no damping. We can crank this up to infinity if you want. You can actually type infinity into it, and then your object won't move at all. But if your object is moving too quickly, you can increase the drag. And you see the object is now moving a whole lot more slowly, because it's being resisted on every frame by the amount of drag that we have applied. So let's go ahead and set that back down to 0. Now, drag itself just applies to linear motion, literally moving through space, going from point A to point B. You also have angular drag, which is going to resist how well the object can rotate. So as we crank this up, it becomes harder for the object to spin, which is not going to be too visible when it's actually hitting a surface and coming into collision with friction and whatnot. To really show that off, we'd have to have some sort of a force trying to apply torque. And so this is kind of like your anti-torque. So I'm going to set this back down to 0.05. Now, next we have use gravity. Check yes or no. It's pretty obvious what that does. If we turn this off and we hit play, what do you expect to have happen?
It's going to float.
That's right. It's just going to kind of sit there until some other force or collision responds to it or exerts something to it. Next, we have is kinematic. Now, this is kind of cool. If you are a Maya person, because I love throwing these out, if you're a Maya person, this allows you to designate a rigid body as being passive or active. And if you're not a Maya person, then you're wondering, well, what does he mean by that? Don't worry, I'll now explain it. Let me take our little object here, and I'm going to get it away from that hill, because I really don't want it to just roll away into nowhere. Let's see, if I hit play right here, what's it going to do? Is it just going to kind of sit there on the ground? Yeah, that'll work. Now, is kinematic allows you to designate whether this object is moving because of physics simulations, or is it moving because of some other means, like keyframe animation. For example, if I create another rigid body relatively quickly, let's go create another cube, and now this already has its collider and everything, so let's just go to component, physics, and let's drop on a rigid body. And I'm going to take this and I'm going to scale it, make it kind of wide. Let's get it relatively close to the ground. Line it up kind of like so. Now it is a rigid body. I haven't given it a physics material. We'll go ahead and do that just for sake of completion, though it's not really all that critical just for what I want to demonstrate. I'm going to start off just by hitting play. And if we take a look, that box just tumbles to the ground. You'll see it's very bouncy. And it'll eventually come to something that remotely resembles rest. But if I check is kinematic, and I turn and look at it, it's not doing anything. because right now it's waiting for me to move it through some other means, such as keyframe animation. So I could, just if I wanted to, and this is I know this is kind of a little bit above and beyond, but we could animate this guy. And we'll just call this block animation. And I'll drop, let's see, what axis will we be moving in? It looks like X to me. So we'll drop on a keyframe in X, and over 1 second, we'll just move over here. And that should give us something, so we'll go ahead and stop recording, close, hit play, and have a look at what we get. And he just pushes that object right out of the way.
Right. Just because he's marked as is kinematic, he doesn't react to physics himself, but he does impart collisions and force on other objects that it hits.
Right. Now, we don't necessarily have to do that. If all we want to do is push an object over, the collider is already going to make that possible. The trick here, really, what I just showed you is nothing all that special in terms of rigid bodies, but I just wanted to kind of throw it out there to get you thinking in the right direction, because the whole idea of having the is kinematic checkbox is that you can turn it on and off with scripting. So if you have some object that you're physically moving through the scene, it could be maybe, I don't know, a car, a vehicle. It could even be a character. You could have a character that is running around, arms and legs, and it could have rigid bodies that are on each major bone of the body. Then at some point, if that character dies, you needed to turn into a ragdoll or suddenly get floppy, you could activate is kinematic. It will stop listening to whatever behavior was already driving it forward, and it will suddenly be simulated. The physics engine will take over, and it'll collapse to the ground and roll around. And I'm not necessarily talking about like a playable character either. I mean maybe some other character.
Like an AI type character.
Yeah, that's kind of walking around on the scene that you suddenly need to turn into a ragdoll and collapse to the ground. You could use, in scripting, is kinematic to trigger the moment when it should go from manual style motion to the simulated style physics motion.
So the moment you turn is kinematic off, it's now going to be driven by the physics engine.
That's right. Now our next property is interpolate. This is a corrective feature. This is one of a few properties you're going to run into while you work with physics objects inside of Unity, where if you don't need it, so much the better, but it's good that you know what it does. If you have a situation where you are experiencing some jitter or some shake, if you have a really extreme kind of motion in your physics simulation and you're noticing problems in it, you can switch on interpolation. And what it's going to do is, as the name suggests, as the word interpolate suggests, it's going to try to smooth out the overall result. It has two separate modes. It has interpolate and extrapolate. And to show what this is going to do, or to try to illustrate an example of what this is going to do, let me bring up my whiteboard here, and I'm going to jump over to my layers. I need a new layer. I need a new piece of paper. So to really make this make sense, we need a timeline. And I'm going to jot a couple of notes down. Interpolation. Used if there are motion problems. Such as jerkiness. And again, it has two modes. First, it has interpolate, and it has extrapolate. And you can think of this little line I've just drawn up here as time. And so here are all of the different frames at which we have calculations taking place. And let's just consider this frame to be where we are right now. Interpolate is going to reach to the frame we were previously, just before where we are now, and it will create a smooth blend from that point to our new point. And that will help alleviate jerkiness. It's blending from where we were to where we are. Extrapolate is a little special. It's actually going to look ahead to where we should be on the next frame, and it's going to blend from where we are to that. So you just choose one of those two modes. I would try interpolate first and see if that solved your problem. And then if you're still experiencing jerkiness, try extrapolate. If neither one of those are solving your problem, you may want to reconsider your simulation. Try taking a look at maybe applying a little bit of damping, Maybe objects are moving a little too quickly and it's causing some erratic behavior, so you might want to slow things down. It's just kind of, well, it's one of those things, and a lot of physics simulations you come up with are going to be that level of trial and error.
Yeah, because this system is a best guess, some of the numbers that you dial in can yield some really weird-looking results.
This is true. This is true.
The most notable one, though, is when you get objects collisions where an object just gets sent off into space.
And that's something we're actually going to discuss here in just a moment. Now, our next property is freeze rotation. If you switch this on, your object will simply no longer rotate. Rotations just aren't being calculated for it anymore.
A good use for this is, let's say you have two objects that are colliding, but you have one that you want to be so massive that you don't want it to impart any spin. Think of an example. Let's say you had a kitchen table and you dropped a dish on it. You want the dish to rattle around, but you don't want the table to rattle around or start spinning. So you can turn the freeze or rotation on, and that table will not spin.
Absolutely. Now, what I'm going to do real quick is I'm just going to put this sort of to the test. We're going to take our little box. Let's move it over here. Now, I've actually locked the rotation on it, or I've hit freeze rotation, and now we'll watch it, and you'll see it just slides down the hill now. It's not actually rotating at all, and that just kind of drives that home. Now, our last property is collision detection. Now, this one is one of those really technical sort of properties, and it kind of goes back to where we were with interpolate, where it's sort of an error correction property.
Right, and unfortunately, this is one of the ones that we can't demonstrate easily.
Yeah, not easily. I probably could if I started doing crazy things, but for sake of system stability, I'm just going to draw it out for you, because it's really easy to understand once you know what it's there for. So, collisions can be an interesting thing. Also, I just want to mention, just before I go any further with this, also, just like with interpolation, this is a corrective force. If you're not experiencing any problems, don't mess with this. Leave it alone. Leave it at the default settings. Because you might be thinking, I'll get to why here in just a moment. I don't mean to talk in too many circles, but we'll get to that. Collision can run into problems if you have objects that are very fast. And I'm just going to make very in all caps. Because in a lot of cases, a fast object's just fine. It depends, it's all relative. It depends on what you think of as fast. But a really good example would be a bullet. I think this is just the classic for this kind of calculation. You have a little gun, and it's going to fire some kind of a bullet. And this may or may not be the kind of thing that you would ever simulate using physics. But let's say you are trying to shoot at some target. The problem with this simulation is that bullets move very, very, very fast. And it's entirely possible that over time, the time actually used to make calculations, we might have a calculation with the bullet at this point, and then our next calculation, if we're really lucky, might have the bullet at this point. So here's our little bullet. And then the next calculation would take place with the bullet already being over here. We just didn't have any calculations during this whole range.
But it completely missed the object we're trying to detect a collision with.
That's right. You do not have constant calculation taking place. It's not infinite calculation. It has to be broken apart. As a matter of fact, it's generally going to be taking place less frequently than your game's update cycle, using, what is it called?
Fixed update.
Fixed update.
Right.
I keep wanting to say stepped update, but it's actually called fixed update.
Right, where a regular update is running as many times a frame as it possibly can get going, or in a second. So if your game's running at 60 frames a second, you've got 60 updates.
Mm-hmm.
Now, with fixed update, there's a value which we can set, so it only runs, I believe, at by default about 10 times a second.
That's right. We can change that in the time settings inside of Unity. So if we jump over to Edit and go over to Project Settings, take a look at time, you can see your fixed time step.
So
now I'm going to jump back over to Photoshop. There are several different things to take into account. You've got your calculation iterations. You have what level of penetration is allowed before you throw back an interpenetration error. Of course, you have the velocity of the object to take into account. You have your fixed time step that's being taken into account. So many different factors to control. But if you have something that is going so very quickly that it is passing through objects and not colliding, then you run into this setting. As I come all the way back to my rigid body, we have our collision detection. So we have three different properties here, or three different settings. We have discrete, continuous, and continuous dynamic. Now, let's just start off with discrete. Simply put, this is for standard normal collisions. This is your default value, and if you can leave it here, so much the better. Don't change it if you don't have to. Now, the next one I'm actually going to talk about, I'm going to skip one. We'll go down to continuous dynamic. This is something that you would put on a very fast object. So you would take your bullet and you would set its collision mode to, or collision detection mode, to continuous dynamic. Now, the object that it needs to collide, that would actually receive continuous.
Right. It's not moving, so it doesn't need the dynamic part of it.
Yep. Let's say this is the object that the fast object will hit. And this is all just kind of a theoretical example just to illustrate why you have these settings. I don't think there's really going to be a situation where you're going to be trying to simulate a bullet with physics.
Right. There are other techniques that require scripting that you would use that are much more accurate.
Right.
Because even continuous dynamic continuous can still miss.
Absolutely. And, I mean, if you're really doing something like a bullet, I mean, in most cases for a game, you're not even going to simulate a bullet. You're just going to do a ray cast and assume that the whole thing took place instantaneously. But if you have some object that is moving along at just a blindingly fast speed and you're having a hard time causing collisions, then come back to these settings, switch it from discrete, take your fast object and set it to continuous dynamic, and the objects that it needs to collide with you would set to continuous. Just realize that these other settings come at the cost of some overhead. So whenever you can, just use defaults. As a matter of fact, if it's not critical to have the object going quite that fast, it might be a good idea to consider slowing it down first.
Right. And if, like we were mentioning with bullets, if your object's just getting that fast and you have to have it, start looking at raycasting instead.
That's right. Now, that covers all of the properties of rigid bodies. So we've taken a look at what rigid bodies are. We've talked about what's required to make them, being a rigid body component, a collider. It's also a good idea to have a physics material and some sort of a mesh. We've talked about their setup with adding on a rigid body component and a physics material into that. And then we talked about all of the rigid body properties being mass, drag, angular drag, whether or not you want to use gravity, whether or not the object is kinematic, the interpolate property, which allows you to smooth out your animation if you're seeing any kind of jerkiness in the overall simulation. We have freeze rotation, which will prevent any rotation from being calculated. And finally, collision detection, which allows you to correct errors you have on the collision of very fast objects. That is everything I wanted to cover in this video, and that will wrap things up. Thank you very much for watching.